Hi and welcome to a 3DE4 tutorial. This course is all about discussing lens distortion of a GoPro Hero4 Black. We will see the surprising complexity of handling lens distortion caused by a GoPro lens. And we'll learn how to handle these effects with the help of two different shots. First, we use classic grid shots to determine lens distortion, then shots of a green screen to adjust focal length. In the last chapter, we will export one shot to Nuke. Alright. Let's begin with an overview of the huge amount of different video modes a GoPro provides. In the official manual, we can not only see multiple resolutions, but also 3 different field of views and 2 different aspect ratios. And on top, each combining differently with the others. Well, that looks like trouble. Let's have a quick look at some of these different modes and how they differentiate. In this project we do have 9 shots, each shot with a different video mode. When going through these frames, we quickly see how the different angles affect the look of the green screen. In addition to that wild bunch of images, even shots with the same angle and aspect ratio are different. Let's have a closer look at shots 4K and 2080 wide. According to the manual, both video modes record with angle wide. Aspect ratio is 6:9. So, in theory, both frames should show the exact same image. Of course, only resolution should be different. However, their content is definitely not the same. Looking at the bottom, we see shot 1080 wide seems to be stretched, resulting in points moving out of the field of view. It's difficult to guess why this happens. Maybe pixel aspect is unlike 1 for at least one of the 2 shots, but foremost, when seeing such an effect, a slight lens center offset comes into mind. More details about this offset issue in the next chapter. Well, it's becoming more and more obvious that even the camera just has a single physical lens built in. One lens in 3DE4 won't fit for all modes. Instead, we have to create and adjust individual lenses for each shot. In the next chapters, we will do this, focusing on 6 video modes covering every angle and aspect ratio with at least one shot. Let's have a look at the chosen shots. In addition to the 6, this project contains a mysterious 7th shot, which will be shown later in this chapter. So be patient, it's worth it. We notice there are 2D tracking points already tracked in each shot. Yeah, quite a lot 2D points across all frames. Last, multiple lenses were created, named, and assigned to their respective camera. That's all for preparations. You might guess, setting up such a project with so many cameras, lenses, and tracking points took some time. So here's our little gift. You can find this project as a 3DEqualizer merged file, along with all images within the GoPro tutorial data in section Download at 3DEqualizer4.com. The link to the archive is in the description of the video below. Alright then, let's start with focusing on lenses. Select one of the lenses, for example the 2.7K lens, and have a closer look at parameters film back and focal length. These clearly aren't 3DE standard values, so where do they come from? First, film back. Unfortunately, there aren't official docs from GoPro. But several sources on the web are hinting GoPro 4 features a 2.3 inch type sensor with an aspect ratio of 4:3. The dimension of this sensor type is 6.17 by 4.56 mm. So, can we set the film back width in all cameras? Having a closer look at angles wide, medium and narrow? Better not. When going through them, we quickly get the feeling these aren't angle modifications by the lens, but simply a digital zoom. Therefore, actually, we would have to adjust film back since all these angles probably use different areas of the sensor. But who can say for sure which exact areas were used? So we have to stick with the entire dimension for our shots and see what we can do later in adjustment. Okay, next, focal length. Luckily, there is an official support document about this topic. In this doc, GoPro states focal length equivalent values for all 3 angles. We can assume Equivalent here means in relation to a full-frame sensor. With a little bit of math, we get a factor of 5.64 between the full-frame and the 2.3-inch sensor. With a tiny bit more magic in math, we can calculate a focal length for angle wide of 2.482 millimeters. Quite a reasonably value for such a small sensor. Okay, sounds good so far. The site also provides information about horizontal and vertical angles. Our selected lens belongs to a frame shot with FOV wide and aspect ratio 4:3. So let's find this type in the table. Comparing its angles with these in 3DE4, we quickly see the values aren't matching, although we use the exact values for film back and focal length. So where's the mistake? Either the sensor size is wrong, or focal length here is just an approximation, or, this might be the most plausible explanation, all FOV values in the dock simply are defined differently than in 3DE4. For example, distortion values could be included into angle calculation. But of course, that's something only GoPro can answer. However, we can see even official specs might not be precise enough or not defined suitably for our purpose of adjusting a lens and lens distortion. So, what to do with this dock? Burn it? Maybe. But in its defense, at least these values indicate an approximate starting point for adjustment. And that's definitely better than nothing. So we roughly set up the lens. Now it's time for lens distortion. The best method for adjusting distortion parameters is using a grid shot. But where do we get grid shots for our shots? Well, they are already imported and assigned to each camera. Didn't see it? To be fair, it's not obvious since they were imported as proxy material. In Attribute Editor, simply set parameter proxy footage to alternate number 1. And here we go, a nice classic grid shot appears. Let's set this for the other cameras as well. Enable toggle button Show Matrix and have a look at it in all cameras. Very nice. So, straight ahead to adjustment. Let's hide the matrix for a better view at the grid. Having a closer look at the grid shot, we see huge distortion effects, kind of looking like a fisheye lens. Well, if it looks like fisheye, and 3DE4 specifically has a distortion model for it, we set parameter lens distortion model to fisheye. A quick but important tip for this distortion model. Unlike all other models, focal length here is a distortion parameter and crucial for a correct adjustment. When activating toggle button undistort, the influence of focal length becomes obvious. If left out of the adjustment, it is not possible to get correct distortion values. Again, this only applies to distortion model fisheye. Alright, for adjustment, open Calc, Distortion Camera Geometry. Add focal length to the selection. Then hit button Calc Lens Parameters. Oh boy, that doesn't look good. Let's have a closer look at the possible errors stated here. Well, all matrix points are set correctly. We have to adjust focal length, even a classic grid shot is being used. So maybe this might be indeed the wrong model for this shot. But what else than fisheye could it be? Well, in case there really isn't a fisheye lens built into a GoPro camera, we can assume it's simply a standard radial lens, just with huge distortion. If so, let's try distortion model standard degree 4. Open again Calc Distortion. And start the calculation, this time of course without focal length. Parameter values look reasonable, but calculated deviation is a catastrophe. Maybe additional parameters might help, but which of these makes sense to be taken into account as well? This is explained quite fast. In the beginning of this course, we saw an issue with slightly different images, although both were shot with the same angle. Well, according to the manual. The best explanation for this issue is a lens center offset. When thinking about the incredible small size of a GoPro camera, the difficulties to engineer and produce such a camera selling it with this low price, it's not impossible to assume some error margins during production, which of course is common for every object built from multiple parts. But having this tiny lens and sensor, even a misalignment of a tenth of a millimeter between image sensor and lens has a measurable impact on distortion. The result is all rays from the radial lens do not meet in the center of the sensor, but beside it, causing an uneven distortion across the image. So, the lens center is unequal to the image center. And this is corrected by parameters lens center offset. Please note that unfortunately, this offset most likely differs for each manufactured camera, so might have to be adjusted for each camera individually. Enough theory, let's try it and add both parameters to the selection. Then again, calc lens parameters. Well, that's disappointing. All this talking and no improvement. It looks distortion model radial degree 4 is not the right one either, but we have some other models left to try. To the next one then. Choose Anamorphic degree 4, then calc distortion. Although used primarily for anamorphic lenses, we try this model on our radial lens simply since it provides more distortion parameters suitable for radial lenses as well. Therefore, 3DE4 has more possibilities to correct distortion effects. We still assume it's a radial lens, so parameters lens rotation and squeeze X can be deselected. Calc lens parameters, and we see we still got a bad result, but at least this is not a total catastrophe like in the previous attempts. Again, let's add both lens center offset parameters. Great, deviation was reduced further. We have a new low record. It seems we are on the right way. We clearly need the offset parameters, but we are still a bit away from the finish line. There is one model left, so maybe the lens is really that weird that we need much more parameters and go full nuclear on this shot. Calculating with the classic LD model makes no sense at this point, since it provides even less parameters than radial degree 4. So choose Anamorphic degree 6. Then calc distortion. We see there's really a huge amount of parameters in the list. At first, for a better comparison, let's calc only distortion parameters. Approximately the same result as before with degree 4. Again, let's add lens offset. And here we go, the best result we got so far. Deviation value is not perfect, but quite good considering focal length still might not be correct. Remember, we got this value from the support doc alone. Transfer all parameters to the lens. We have a calculated lens. Let's check the result visually by displaying the grid undistorted. Looks good. The checkerboard is distortion free. Even in the corners of the undistorted shot, all clear and unbound. We have solved the first shot. The next is already waiting. Set camera 2.7K. The first thing we notice is the different aspect ratio. Shot 4K Super View was 6:9, this 2.7K shot is 4:3. Remembering the aspect ratio of the sensor, maybe this video mode uses its entire surface. This means new image, new rules. We cannot say for sure if the previous LD model suits best here as well. At least we can assume distortion model Fisheye also won't work here, since there isn't a true fisheye lens built into the camera. But maybe radial degree 4 fits better this time. So leave the model untouched and open calc distortion. As mentioned, this shot seems to use the entire sensor surface, so lens center offset might have no impact this time. Calc lens parameters, and we see, well, not bad. But again, considering the clear grid shot, this value is a bit too high, even with a possible false focal length value. Okay, then add both offset parameters and calc again. Unfortunately, no improvement. Well, we clearly are in experimenting mode, so skip degree 4 and switch directly to anamorphic degree 6. At first, calc again without offset. No, even worse than with radial 4. Okay, one last try with both offset per meter. Wow, that's a great result. Seems we have a winner. Let's have a visual check, so undistort the image. Perfect. Again, no distortion in every corner. Now, why did we need a distortion model with an insanely amount of parameters to calculate distortion? It strongly looks like the lens built into the GoPro simply is a not really high-end, non-standard lens, generating truly weird distortion, and therefore needs a lot of parameters to correct all of its weirdness. Another explanation might be a possible image manipulation behind the lens, meaning software-based distortion, adding to the distortion of the physical lens. Each distortion individual might not be complicated, but combined, well, we saw it. Oh, on top, let's not forget, this camera has a lens center offset. At the end, all we can assume is this untypical distortion is a combination of all these aspects. The only thing we can say for sure is distortion model Anamorphic degree 6 in combination with lens center offset will do the trick. Alright, there are 4 shots left for adjustment. Let's continue the way we did it with the first 2. Okay, we have 6 shots with calculated distortion values, each showing a nice distortion-free checkerboard. Good job! In the next step, we finally have a look at the mysterious 7th so far unconsidered shot. Set this camera and select its lens. Unlike before, here we see a true fisheye shot. The first thing to notice is the bulge within the image is way stronger and more radial than in the previous shots. Of course, a matrix was already set here as well. Fisheye is set as distortion model, so as we learned, we have to consider focal length since it's the distortion parameter in this model. Playing with focal length, we notice that we can adjust this parameter roughly by hand. So let's do that. Maybe we can find a value to undistort the grid. Not so bad, the checkerboard is almost distortion free. Well, almost. Of course, this can only be used as an approximation, but every hint for 3DE4's calculation core is valuable. Let 3DE4 take over from here. Open Calc Distortion and add focal length to the selection. Then calc lens parameters. Okay, again a bad result. As we can see, there are not many options left. Maybe famous lens center offset can help again. Add them to selection and calc again. Alright, that's a great improvement. Let me explain. First, the fisheye lens used in this shot is also not really high-end. The individual lenses inside the lens might be slightly decentered to each other, but it suffices for demo purposes. Second, and more important, a fisheye lens with its massive distortion is much more sensitive to lens center offset. Therefore, it's always a good idea to try calculation with and without the offset parameters and compare its impact. Okay, transfer parameters to the lens, and let's have a visual check. Great. The slight angle in Y direction was clearly caused by the camera's alignment. But apart from that, we have an even, unbowed checkerboard. Zooming out, we can see how much the image has to be transformed for undistortion. Quite impressive. One tip at this point. As we can see, undistorting something extreme like fisheye causes some display areas in 3DE4's display area. That's because 3DE4's display area is optimized for speed, for displaying image transformations in real time. To prove that these aren't wrong distortion models, but simply an OpenGL optimization issue, let's quickly transfer this project to Warp 4. Here we can find all shots and, more important, all lenses with their values correctly transferred. Expand the visible area, the so-called overscan area, to see as much as possible of the undistorted image. 10,000 by 7,000 pixels should be suffice. Okay, everything's prepared, so click on Preview. We can see no display errors here. Warp 4 is clearly optimized for quality, but we saw as well the higher quality was achieved by a much longer computation time to transform the image. But again, this issue simply occurs having images with massive distortion. Perfect. We have calculated distortion for all our 6 GoPro lenses. In the next steps, we will use the green screen shots to adjust focal length. Before we start, a quick note. Beside 2D points tracked in all cameras, there's also survey imported with vertices assigned to their respective 2D points. With all these cameras in the project, it is easy to lose overview, so let's calc one camera after the other. Disable all cameras except 4K Super View. Great, calc the project. Well, that doesn't look good. Didn't grid shot adjustment calculated a deviation of roughly 2 pixels? Since we have survey, let's check the result in lineup controls. Disable the cameras in the view. Okay, we quickly see 3D model and footage aren't matching at all. Deviation gets stronger, especially towards the edges. As we already assumed, the focal length value in the GoPro support doc is an approximation to the real value and needs to be adjusted in each lens. Open parameter adjustment. Then add focal length to it. And increase the number of samples. Further, although we can assume we are already near the correct value, this tiny range of 0.5 mm may be too small. Increase it a bit. Yeah, that should be suffice. Hit button, adjust. Cool, the result is already quite an improvement. To fine-tune it, let's give it a second try with Method Adaptive. In contrast to brute force, Method Adaptive is not bound to a fixed amount of samples placed evenly across the range. So if the true best value is between 2 of the current sample points, it has a chance to find it there. Switch adjustment method to Adaptive and adjust again. Well, not a great improvement, but now we can be sure we found the best value. Let's calc the project. Okay, deviation went down by factor 6. That's not bad, but the result is still not good either. Looking at footage and 3D model, we can see there is still a lot of discrepancy. The explanation is quite easy. We calculated distortion values without any focal length, then adjusted focal length without distortion values. So there's probably a need to balance all parameters for a better result. In order to do that, add all of the distortion parameters to parameter adjustment. As well as both of lens center offset. We can assume these values are approximately in the correct range, so set adaptive all, then adjust. Adjusting so many parameters takes some time. Each parameter can interact with each of the other, which exponentiates the calculation possibilities. Great, deviation went down by circa a third. A quick advice: with such a huge stack of parameters, the adjustment course sometimes needs a second try to refine all these for finding the best values. Of course, we can never be sure how much it will improve, but it's always worth a try. Okay, we got another 10%. Transfer all parameters to the lens. Then calc the project. Have a look at the result in lineup. Much better than before. Especially deviation at the edges was improved dramatically. Perfect! Finally, we really solved this weird shot. Do not waste any time, there are still 5 others waiting for us. Clear parameter adjustment. Set the next camera. Enable it. And of course, disable the previous one. Again, what's the status quo for this camera? Well, history repeats itself. Okay, a history a very short while ago, but still repeating. Although we adjusted all parameters together in the previous shot to achieve the best result, it's not a bad idea to adjust focal length alone again. Having all parameters at least near their best values can speed up the adjustment tremendously. Alright, again, increase the separate and range. Then fire button, adjust. Like previously, switch again to adaptive to find a possible better value between the current samples. Great, also a fantastic deviation value, roughly 90% down, with focal length adjustment alone. Okay, transfer parameters and cut the project. The result is already pretty good, but as we saw earlier, we still have a great chance to improve even further by adjusting all parameters simultaneously. Yeah, it's a lot of clicking. Adaptive all. Then adjust. Awesome. Deviation was halved. Like we learned earlier, adjusting a second time can improve even further. But for this video and for the sake of its length, this result is really acceptable. Have a quick look at the result in lineup. That's really a shot we can deliver. Even at the edges, all 3D reconstructed points and survey is glued to the markers. Good job. 4 shots left, we do know the routine, so let's continue. Welcome back, folks! Having all shots adjusted, what are the final results? Besides 4K Super View, all deviations are below 1 pixel, which is fantastic. And even 2D pixels for the 4K image is acceptable considering its high resolution and weird distortion. Well, seems we have done our job and made his supervisor happy. The last step, like always, exporting the result. As an example for all shots, we are going to export the distortion data of our fisheye lens to Nuke. So set this camera, then select 3DE4, File Export, Export Distortion to Nuke Grid Warp. For a more detailed explanation of this export tool and other ways to export distortion data, please have a look at tutorial Lens Distortion Pipeline, which can be found in the tutorial section at 3DEqualizer4.com. Set a file name, and as previously in Mob 4, increase overscan resolution. Great, switch to Nuke. The footage was already imported and connected to the viewer. Import the node. As we can see immediately, obviously there's something wrong with the image. It gets weirder and weirder towards the edges. Grid Warp divides the image into a grid and transforms the image according to its vertices. So, with only the default 11x11 vertices, it's hard to handle such a strong deviation. The vertices have to be transformed enormously, forming these huge rectangles at the edges. But maybe, if we increase the amount of vertices, we're getting a better result. Back to 3DE4, and again, open Grid Warp Exporter. Increase the resolution to the maximum of 19x19. Set a new file name. And again, set a sufficient overscan resolution. Finally, export the node. Back to Nuke. A little preparation. Let's copy the read node so we can compare both results. Then import the new node. And connect it to the viewer. We see a little improvement, but not a good result. The increased amount of vertices clearly correctly undistorted a bigger area, but it's still not enough. Seems good old Grid Warp really fails at this fisheye shot. So what other options do we have? The Lens Distortion plugin kit, downloadable at 3DEqualizer4.com. How to install this kit for using it in Nuke? Please have a look at the detailed installation instructions in the article. Well then, let's try LDPK. In the export menu of 3DE4, select Export Nuke LD 3DE4 Lens Distortion node. Set a file name and export the node. That's all. Back in Nuke, again let's copy the read node, then import the new node and connect the view to it. Unlike Grid Warp, LDPK doesn't have an overscan feature included, so Nuke has to help us here. Add a reformat node and set the output format to 10,000 by 7,000 pixels. Of course, the footage should not be resized. Et voila! Perfect! Even at the edges, clearly a correctly undistorted image. That was quite a journey, right? We learned about all the different video modes of a GoPro camera, about the differences and difficulties considering their distortion, and about the trustworthiness of specs found on the web. In 2 steps, we adjusted distortion data for 6 video modes, covering every angle and aspect ratio, using grid shots and normal shots of a green screen. Further, we saw a true fisheye shot and learned about its characteristics to distinguish a fisheye shot from shots with simply huge distortion. Last, we exported data of a solved shot to Nuke with Grid Warp and LDPK. Well, that's it. Thank you very much for watching. I hope you enjoyed this tutorial.